So yeah, I'm going to talk about some joint work with Martin Albrecht. This will be at Eurocrypt, the delayed Eurocrypt happening next month. So this is motivated by side channel attacks. So in a side channel attack, an attacker uses some kind of external information like timing or electromagnetic radiation or something else to learn some secrets from a cryptographic implementation. So it doesn't matter how good your proofs are if the implementation doesn't do it right. So here's a couple pretty pictures from sample side channel attack papers. And then the sort of mathematical interest of these kinds of problems, for me at least, is that in a lot of practical attack scenarios, the attacker doesn't actually learn perfect information about the cryptographic secrets. They only learn partial information. And then the question is, from that partial information, can the attacker actually reconstruct full secrets and fully break the system or not? So empirically, like one thing that seems to be a little bit interesting is some cryptographic algorithms are either harder to implement securely or more easy to exploit mathematically than others. And in particular, ECDSA and DSA, but more people use ECDSA signatures, are a favorite target for side channel attack research because an attacker only needs to learn a small amount of signal per signature generated in order to learn the full secret key. And this is because of the sort of nice linear structure of the algorithm. So I think everybody's seen this before, but just to make sure that we're all on the same page, sort of ECDSA, you have some global parameters, you have a group of order n, it has some generator g, your private key is an integer d, your public key is, say, d times your generator, and then to generate a signature on a message hash, we just have the hash, we don't care about that. The interesting thing about ECDSA is that it requires a per signature nonce, which is actually sort of an ephemeral private key. This is some integer k. And then the signature has two parts. It has, say, the x coordinate of k times the generator, and then it has this nice linear portion which is generated from k inverse and the hash and the long-term secret key and the first part of the signature. So we've got these two pieces. And the concrete attack model to keep in your head is that the attacker learns some information about the signature nonce k by observing the signature generation process. So if the signature generation process requires some curve operations that go bit by bit through the secret k, and the attacker can view different operations based off of the different bits, then they can learn the integer k. Or maybe it goes bit by bit, but if it starts at the least significant bit and sort of ends and the most significant bits happen to be 0, then it's not going to do anything, and it's done, and then the attacker could see how long the secret nonce k is. So those are some concrete examples. So just to start at a very easy level, hopefully everybody knows this. So if the attacker knows the secret nonce k fully, like they can just view each bit of the nonce k, like read out, oh, this is a 1, this is a 0, this is a 1, this is a 0, then it's trivial to recover the long-term secret key. You just rearrange the S part of the signature, and then you can solve for the long-term secret key. So you're dead in that case. More interesting is if the attacker is only learning a small amount of information per nonce. So in this case, you have, say, a few most significant bits of a whole sequence of nonces for many signatures. And it turns out that you can recover the secret key efficiently. There are two algorithms to do it. I'm going to focus on the lattice-based algorithm for this. So this has been known for quite a while. It is a fun technique. So this is based off of the hidden number problem. The hidden number problem was formalized by Bonet and Venkatesan in 1996. They were originally applying it to Diffie-Hellman, but it turns out that DSA and ECDSA are easier to attack in practice. So the hidden number problem, it's kind of a one-dimensional LWE. We've already seen that today, but we have a secret integer alpha. We have a public parameter, which is an integer n that's going to be our modulus. And then we get a bunch of samples, so I'll call these samples, and then each sample corresponds to a pair TI-AI, and so the TI is a multiplier, and you take TI times alpha mod n, reduce that as an integer, and output, say, the most significant bits, which is the AI. And then the desired output of this is to solve for the alpha value. And you can look at this as a system of under-constrained linear equations if you would like. So we have some unknowns, say the ri's are the least significant bits of this Ti alpha. Then say we have the ai plus ri is the Ti alpha. And then we have the system of equations, and say we know the ri's are small, we know the alpha is full size. We have one more unknown than equation, so we can't solve this, but if the ri's are sufficiently small, we would expect there to be a unique solution. So the question is, how do you find this? And just to sort of put this in very concrete terms for the ECDSA signature recovery problem, this is exactly the problem that we're trying to solve when trying to break ECDSA in the context of a side channel attack. So we just write out the coefficients in terms of the signature values that we know as the attacker. So the sort of standard lattice algorithm to solve this is you construct a lattice, you look for a short basis element, and then hope that's your solution. So the usual approach, we have our input equations here. We construct this lattice, which I won't go through all the details. This is sort of a modified version of the Boneh and Venkatesan construction. So we have like row vectors here, and then, oh, somehow this is like getting cut off. Oh well. So we have a target vector that we hope to find, which contains our solution. And we know by construction that this is a short vector in this lattice, and we hope that it is the shortest vector, so it would be easy to find by using some lattice reduction algorithm like, say, BKZ. So in order to verify that this works, we can compute some of the parameters about this lattice. So we can compute the determinant of the lattice. We know the length of our target vector based off of the bound on the size of the elements that we're looking for. And then we can ask for the expected length of the shortest vector in a random lattice using the Gaussian heuristic. And it's that. And so if the length of our target is like less than the Gaussian heuristic, then we would expect that to show up in, say, a BKZ reduced basis. And so then we can use the BKZ algorithm to find the solution. And if it's larger, then we wouldn't necessarily expect it to show up in a reduced basis. We would expect the reduced basis to be full of the kind of random spurious non-solution lattice vectors that wouldn't actually solve our problem. So that's kind of the hand-wavy version of the analysis here. Okay, so this technique is super popular. So here's a random selection of papers that are attacking real systems using these algorithms. And most of these are using ECDSA, but I did put in the raccoon attack, which applied it to Diffie-Hellman for the first time in practice, which was kind of fun. So there are a number of papers that sort of make the point that there's a limit to how well these lattice algorithms work. And I took a sample quote from one of these papers. There's a hard limit to what can be achieved using lattice reduction due to the underlying structure of the hidden number problem lattice. It is impossible to attack ECDSA using a single bit non-sleek with lattice reduction. In that case, the hidden lattice point corresponding to the HNP solution will not be the shortest vector even under the Gaussian heuristic, so that lattice techniques cannot work. So they're basically pointing out that, like, if you realistically, if you have, say, a 256-bit curve, which is the case that most people care about in practice, and you are asking, can a side channel attacker actually recover the secret key if only one bit of the secret signature nonce is leaked per signature generation, then it's not possible, because you can construct the lattice vector, or you can construct the lattice, you look at the Gaussian heuristic, and basically the upper bound on the length of the vector is never below the Gaussian heuristic for this lattice. So this is what this calculation looks like. So here, this plot is a little bit confusing. So we've got this solid line here is plotting the length of the Gaussian heuristic. So that's the log of the length is on the y-axis. And then we are computing the bound on the length of the target vector for different numbers of bits leaked. So there's like a, let's see, maybe I can use this to point. So this is with learning 3 bits per nonce, this is learning 2 bits per nonce, and this is learning 1 bit per nonce. And so this crossover point, at this point, once we're at larger lattice vectors, we expect this target vector, the expected length is, the upper bound on the expected length is below the Gaussian heuristic. So if we use, say, this many samples, we expect the target vector to be the shortest vector in the reduced basis, and so we should be able to solve this problem. So the point at which we expect this problem to become feasible is given by these crossover points. And so what the argument that I put on the previous slide is saying is that essentially if you look at these parameters, this says that solving a 3-bit bias for a 256-bit curve, we expect to be, I don't know, like 130, 140, like it requires solving shortest vector problem in 130 or 140 dimensional lattice, which is feasible-ish now, but is non-trivial. 2 bits is going to require solving the shortest vector problem in like between 250 or 300 dimensions, which is kind of not really feasible. And then 1 bit, you're just never going to get to that point with a reasonable lattice dimension. So that's the argument that's being made. So the observations that we made in our paper is that this argument is not quite correct, and it is inexact in a way that helps a little bit with practice. So we make 3 observations. The first is that in practical applications, there's still a unique solution. You don't actually need the solution to be the shortest vector in the lattice, because we know that the attacker has the public key for the system that they're attacking. And so a given solution is going to give you a candidate private key, and you can just multiply the candidate private key by the generator and check, is that the public key or not? So this is kind of a nonlinear thing that's not included in the structure of the lattice. And so you can say, well, we know whether we got the solution or not. So actually, we don't have to just restrict ourselves to looking at the shortest vector. We can look through many vectors if we want. We could start enumerating lattice vectors and check whether they're the solution or not. So that's one observation. The next observation is that there's a slight, there was a missing constant factor in the vector length. In order to actually capture the behavior of the lattice, the calculations that people were doing, they were just using an upper bound. So the upper bound just multiply the length of the vector by square root of what you expect. But actually, if you compute the expected vector length, you get an extra square root of 3. And it turns out that square root of 3 makes actually quite a difference for practical parameters. And then finally, there's actually a bunch of optimizations that are inconsistently applied in practice. So a lot of the practical papers, they read through the theoretical papers on this. They have a set of kind of folklore things that they do that aren't systematic and actually didn't have the optimal lattice construction. So we decided to solve this once and for all and be like, look, this is the right way to solve this problem. You don't need to re-implement it from scratch every time anymore. So I'll start with the second bullet point, which is that if you introduce that factor of square root of 3 and look at the expected length of the lattice vector rather than an upper bound on it, then actually the lattice dimensions become much more tractable. So for the 256-bit curve that we were looking at before, to solving for a 3-bit bias, you expect it to become feasible with less than 100 samples. And this turns out to actually be the case in practice. And then for a 2-bit bias, it should become feasible at something a little bit less than 150 samples, and it's 132. So that actually should be feasible. And 1 bits, it's still SVP in between 300 and 350 dimensions is not quite feasible, but it's not that it will never get there. It's just beyond our capabilities at the moment. So that is that's the second bullet point. So for the first bullet point of our improvement, how do we actually search through these lattice factors? We can define this more formally if we want, and so we can define this sort of bounded distance decoding with predicate problem. So we have a nonlinear predicate that's not captured in the lattice, and we just want to basically find a vector within a certain radius that satisfies our predicate. And we can also define this with a unique shortest vector if we want. So concretely, the algorithm that this induces is basically every lattice point corresponds, like in our particular application, every lattice point corresponds to a candidate private key, and our predicate is compute the candidate public key and compare it to the known public key. And so we will, in order to solve this problem, we will sieve or enumerate lattice vectors until we find like one of these where the predicate evaluates true, and that will be our solution. So for enumeration with predicate, a lattice enumeration algorithm can search exhaustively within a given radius. And so we can just take an existing implementation of a lattice enumeration algorithm and add a predicate. And instead of just looking, most of them are asking to, like, say, find shortest vectors. Instead of looking for the shortest vector, we actually just ask, is our predicate true or not? We have bounds for how long this takes. So it is exponential in this amount of time. And we can bound the number of calls to the predicate also. You can also look at lattice sieving. So we can augment the sieving algorithms with a predicate. The thing that's interesting about this is that a lattice sieve algorithm will actually produce not just vectors of a particular length, but it'll actually produce a list of all vectors with norm of less than square root of 4/3 times the Gaussian heuristic. And so that means that if when you're using a sieving algorithm, if your target vector is anywhere within this radius, the sieving algorithm will find it in that amount of time. And so you essentially get this slightly larger search radius for not quite free, but free. Yeah?
What are the differences with respect to the version without the predicate? Is it the 0.292 or is it the square root of 4/3?
Sorry, what is it?
What's the improvement over the version without a predicate?
There isn't. We're not claiming there's any improvement. So. So the improvement that we have is that if you are not sort of using this predicate idea, the thing that you do is you use, say, a sieving algorithm as part of a BKZ implementation as a black box, and so then you're restricted to only the vectors that, say, are returned in the reduced basis. So, like, say, you get D vectors for a D-dimensional lattice, and here we can search through exponentially many vectors. So these exponentially many vectors are searched through as part of the running time of running these algorithms, but they're going to be discarded unless you evaluate the predicate on them. So there's no performance improvements. We're using these sieve and enumeration algorithms as we're opening the box a little bit, but not very much. So these are just the running times of the algorithms augmented with a predicate. Other questions here? So yeah, but this turns out, this means that we can search this much larger radius here. So if you want some experimental results, so this is what these things look like. I will try to walk through this. So BKZ sieve and BKZ enum are the algorithms. This was the starting point for kind of the state of the art, applying our optimizations but not using the predicate idea. So this is if you just run BKZ and then say, is our target vector in the reduced basis or not? And so this plots the success probability here. And so we see that the success probability essentially goes from 0 to 1, right about where this is the ratio between the length of the Gaussian heuristic and the length of the target vector. So when this crosses over 1, that's where the probability of success goes from 0 to 1. And then when we add the predicate, we can actually push the success probability much higher for many fewer samples. And so that's the contribution that we have, is that instead of needing 70 samples, we can actually do this with fewer than 70 samples for this particular case. And then if you're willing to spend a lot more computational time, you can use an enumeration algorithm. And here the parameters were adjusted so that it had a sort of 50% success rate, but you can actually just spend exponential time to get 50% success rate with even fewer samples using enumeration. But you see, you actually pay these algorithms are all exponential time, so you definitely pay a cost in the running time. And this is for another case, so you can see that the baseline success rate is here, and we were able to have a much higher success rate. We're able to sort of shove the point at which the success rate goes to 1 further over. The mic go away? Well, you can probably still kind of hear me. So in comparison to previous work, there is a lot of these cases considered in the literature, but people were sort of doing ad hoc things. So for example, running BKZ with arbitrarily chosen block sizes and needing, say, 82 samples. And in comparison, we need far fewer samples. So the practical impact, I mean, some of this you may think like, well, 85 to 65 samples isn't that big of a deal. But in sort of the concrete application of a side channel attack, collecting all the samples can actually be quite expensive. So you might need to do thousands of measurements in order to get like one useful valid sample for the attacker to use. So this can make a big difference in how efficient the attacks are. So let's see, I'm going to skip this slide. The one thing that I want to point out is this case of a 2-bit bias for a 256-bit curve. This should be feasible. It should be doable in 131 or 132 dimensional lattice. We tried to run it and the code crashes, so we are debugging that now. But it should be doable. If the code didn't crash, it should take a couple of weeks. Unfortunately, it takes 5 days to crash on our machines, so it's quite difficult to debug. But I have a student who has been tasked with finding the bug, so hopefully we'll be able to announce a new record in what has been computable with lattices soon. And then for sort of a more fun application, I went back to a paper that I did with Joachim Breitner. We found a bunch of bad ECDSA implementations in the Bitcoin blockchain, essentially by scraping the blockchain for all of the signatures and just opportunistically dumping the lattice attacks at these signatures and finding people who were using nonce lengths of less than 128 bits or less than 64 bits. We were able to compute a large number of Bitcoin signing keys using this at the time, but because we were using the non-optimal construction, we missed some keys. And so going back and using the sieving with predicate algorithm, we were able to recover more Bitcoin keys because of the success rate. So instead of, for the keys with 132-bit nonces, the success rate was almost 0 with the previous work, and we can have essentially 100% success rate for 132-bit nonces, and so we were definitely able to compute all of those keys. So none of these at the time contained any Bitcoin, and we did not steal any. So, but I will say that the Bitcoin and Ethereum and other blockchains are a rich source of implementation errors in cryptography, so that has been fun. So another benefit to this work is it's often thought that lattice algorithms don't cope well with error. And error is something that comes up a lot in the context of side channel attacks because you have inexact measurements. It's really hard to tell whether you had 7 bits of zeros or 8 bits of zeros. And so usually what people do is define some kind of threshold and have some kind of cutoff, but they're discarding a lot of potentially noisy samples, or they might have noisy samples that are included in the lattice where they're wrong about the number of bits known. And so then the question is, how do you do this? And the literature is full of sort of ad hoc approaches to this, like just run it a zillion times with a bunch of different subsamples and hope that it succeeds. And a side benefit of our approach is that we actually have a very natural algorithm to dealing with errors, which is you can basically estimate the error rate and use it to estimate the length of the target vector given the errors, and then use the estimated length of the target vector to choose your parameters accordingly, and then just search further out than you would normally. So even with So normally in the errors, the reason that they cause this algorithm not to work is that your solution is no longer the shortest vector because it's longer than you expect. But if you have an estimate of how long it is, you know how to choose your parameters, and you just adjust your search size accordingly. So this works well. So it had been thought that lattices don't deal well with error, and you need to do other approaches like Fourier analysis that deal better, but it turns out that lattices deal fine with error. So that's kind of the end of my talk. I was not watching the time, so I have no idea what time it is. But essentially the conclusion, you can break the lattice barrier if you're willing to spend more computational time. This paper will appear next month at the postponed Eurocrypt this year. All of our code is available here, so if you ever need to do a side channel attack with ECDSA, we have you covered. And in fact, it has just been extended to include least significant bits and non-zero most significant bits. So more pull requests are accepted. And future work, hopefully we will be able to get the code working for a 2-bit bias on a 256-bit curve. And then other future work, I guess for the people in this room, is are there other applications of this idea? So we had a few other things that we played around with that didn't work super well, but it seems like this is sort of a more general thing, that there's a lot of algorithms where people assume that you're looking for the shortest vector in a lattice, and if you're not restricted to looking for the shortest vector, then what can you find? So, thank you.
Buggy on that one particular case and not elsewhere? Or
we're using the JCCA library like as kind of a black box, and I think it's JCCA and not us. The hypothesis is that it's running out of memory, but it has run out of memory on a machine with 1 terabyte of RAM, so it's somewhere else. It's some memory problem, probably somewhere else in the code, and not like the OS running out of memory. That's as far as we've gotten with the debugging.
It happens to be triggered on this one case and not the other ones, or?
It's just the size of the lattice. So this is by far the largest size that we've done.
One. Okay.
Yeah. So like the most of the experiments that we did were, you know, with lattice dimensions, say 120 or less. And so this was trying to push it to 130 dimensional lattices. And somewhere there it hits some threshold where it crashes.